We have seen how to find and how to use Taylor polynomial of order 0, 1 and 2 for a function of two variables. If we are interested in higher order Taylor polynomials, this is related to Pascal's triangle. If we write once again t0, then this is 1 times the function value, and for simplicity, let's consider x0 and y0 to be 0, so that the expressions are easier and shorter. We assume x0 and y0 to be 0. Then we have seen that t1 was t0 plus 1 times fx at the point 0, 0 times x plus 1 times fy times y. And we have also seen that t2 is t1 plus 1/2 fxx times x squared plus 1 times 2 times fxy times x times y plus 1 times fyy times y squared. So what is new in the next generation of Taylor polynomial is a sum of expressions that have 3 parts: some coefficient, then the partial derivative of the function, times some power of x and some power of y. So we can write it as some coefficient, let's call it Cij, times the partial derivative of f with respect to with respect to x I times, and with respect to y j times. So I j f dx I dy j. That means we take the function and we differentiate j times with respect to y and I times with respect to x. At the point 0, 0 times x to I, y to j. This is the general form of a term, and we add these terms to give the nth generation, nth level, and order contribution to the Taylor polynomial. And if we look at these coefficients, they build a quite nice and easy to describe structure. 1, 1, 1, 1, 2, 1, and this is the top of the Pascal's triangle. By the way, it's a good idea to open Wikipedia, the free encyclopedia, and to open the page Pascal's triangle in Wikipedia. You can also open Wikipedia and to look at Taylor polynomial and partial derivative. Everything we cover here is described quite well in much more detail than we need in Wikipedia. The Pascal's triangle goes on in this form: 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1, and so on. And there's a simple rule how to build these numbers. if you consider two values and add them, 6 plus 4 is 10. And in this way, you can build the lower and lower lines in the Pascal triangle. You take two values and you add them, 6 plus 4 is 10. Or here, 4 plus 1 is 5. You can build the leftmost and rightmost number by considering 0 here. So 1 plus 0 is 1. And what I want to show is that the coefficient here is the number in the Pascal's triangle. So, for example, the third order Taylor polynomial would be T2 plus. And the factor is 1 over I plus j factorial, which is 3. And here we have now coefficients in this line 1, 3, 3, 1. So 1 times fxxx, the third derivative evaluated is 0, times x to the power of 3, plus 3 times fxxy, x squared y, plus 1 more 3, fxyy, y squared, and finally plus 1 times fyy. This is the third derivative of f with respect to y, y, and y, times y cubed. It is easy to show that the coefficients at these terms are just the values from the Pascal's triangle. The values, the numbers in the Pascal's triangle, can be written in the form of a binomial coefficient. And above I is the abbreviation of n factorial divided by I factorial n minus I factorial. By factorial, we mean the product of positive integers from 1 to n. For example, 5 factorial is 1 times 2 times 3 times 4 times 5, which is 120. And the Pascal triangle, as written here, can be written in this way: 0 above 0, 1 above 0, 1 above 1, 2 above 0, 2 above 1, 2 above 2, then 3 above 0, 3 above 1, 3 above 2, 3 above 3. And these numbers do indeed satisfy this summation rule. That means if you add n above I plus n above I plus 1, then you get an entry which is one level down, namely n plus 1, I plus 1. And this is easy to show if we consider what is on the left. Then, using the definition of the binomial coefficient, it is n factorial divided by I factorial n minus I factorial plus n factorial divided by I plus 1 factorial, and the difference is n minus I minus 1 factorial. And when we bring these two terms to common denominator, and we can factor out n factorial, then I factorial, I plus 1 factorial, so we take I plus 1 factorial, and n minus I minus 1, this is greater, so we take n minus I factorial. That means we have multiplied the first fraction by I plus 1, and we have multiplied, that means we have multiplied numerator and denominator. The second fraction by n minus I. But I minus I cancel, and we have n plus 1. And n factorial times n plus 1 is exactly n plus 1 factorial. And here we have I plus 1 factorial and minus I factorial, which is exactly this binomial coefficient, n plus 1 above I plus 1. So the binomial coefficients are exactly the entries in the Pascal triangle. And now we want to show that these coefficients C sub ij are indeed the binomial coefficients. So if we consider just one single term of one single layer or order of the Taylor polynomial, then we want, we can consider the entire polynomial. We want to compare the derivative of t and the derivative of f. And we want to compare corresponding terms. That means if we differentiate j times with respect to y, and I times with respect to x at the point 0, 0, we want to get the same as we consider the corresponding derivative of f. That means j times with respect to y and I times with respect to x. The lower terms give 0 when differentiated, and the higher order terms give 0 when evaluated at the point 0, 0. So only the term of the form x to I, y to j will survive these two operations, differentiation and evaluation at 0. So if we consider some coefficient c sub ij, for which we want to show that this is the binomial coefficient, times x to I, y to j, and we differentiate this j times with respect to y and I times with respect to x. Then, well, let's start with x. Let's consider some example. If we have, say, t is x to 5, then t prime is 5x to 4, t second is 5 times 4, x to 3, t third is 5 times 4 times 3x squared, t fourth derivative is 5 times 4 times 3 times 2 times x, and finally the fifth derivative of this function is 5 times 4 times 3 times 2 times 1, which is 5 factorial. So in general, if we have x to I for some positive integer I, and we differentiate I times with respect to x, then we get I factorial. So when differentiated x to I times, we have I factorial. And when differentiated with respect to x, partial derivative, y is a multiplicative constant. And then when we differentiate y to j times, we get j factorial. And we want this to be equal to this expression, let's call it for simplicity Fij. That means f differentiated I times with respect to the first variable and j times with respect to the second variable. But this gives the relation for the coefficient. This is the corresponding derivative of the function divided by I factorial j factorial. And if we multiply and divide by n, or by I plus j factorial, then we have 1 over I plus j factorial times I plus j factorial divided by I factorial j factorial times the derivative of f. And this is exactly the binomial coefficient I plus j above I or above j. This is the same. So you see, and this completes the proof that when we factor out 1 over n factorial, this is this fraction which is factored out, then each derivative of f must be multiplied by the binomial coefficient n above I, and is the sum of the two coefficients. And these are the numbers in the Pascal's triangle. So at this point, it's finally easy to write, say, Taylor polynomial of order 4. It starts as G3 plus 1 over 4 factorial times, and the coefficients can be read in this line: 1, 4, 6, 4, 1. 1 times f 4 times differentiated with respect to x to 4, plus 4 times f, and it is again 4 times differentiated, but this times 3 times with respect to x and once with respect to y, and multiplied by x cubed y 1 plus 6, and now f x y y x squared y squared plus 4 f differentiated with x only once, and 3 times with respect to y, x to 1 y cubed plus, and then the last coefficient is 1, f differentiated 4 times with respect to y multiplied by y to the power of 4 close. Well, and in this manner it goes on for higher order polynomials.